Stars implode, planets grow cold. Catastrophe is the metabolism of the universe. I can fight monsters, I can't fight physics.
Hello, welcome to GCSE Physics Paper 2, Walking, Talking, Mock and Predictions for 2025. Okay, so let's get started. After being reasonably successful on my predictions for Paper 1, although I could have told you to revise everything, I'd have been 100% successful. So let's see what we can predict or what could come up. So straight away, you've got a question on a required practical. So this is chapter 14, which is reflection, refraction, and lenses, which we'll come to in a minute. So required practical, looks like you got a 6 marker straight away. So describe a method. So let's have a read. Student investigated the refraction of light by a glass block. So you got a protractor used to measure the angles of incidence and the angles of refraction. So when you talk about your method, make sure you include what apparatus you're using. So when you say you're measuring the angle of incidence or measure this angle, say you're using a protractor. Okay, you might think, oh, it's obvious I've drawn it, but when they give the plan to someone, they're not going to give this page to them also. So what is the resolution of the protractor used to measure the angle? So when they talk about resolution, they mean, so here resolution means the smallest reading. Okay, so if you look straight away, the smallest reading here, so that's 1 degree. So that's the smallest thing you can read. Okay, so then they give you a table, angle of incidences, angle of refraction. So they told you they're going from 10 to 60. So describe a method the student could have used to obtain the data in table 1. So you may include a label diagram. Now drawing the label diagram might help. So what I'm going to do, I'm going to use my little post-it note. So here's my glass block. Okay. So first thing you do, so I'm going to tell you point by point, but I'm not going to write it down. You should be able, I'll expect you to be able to write a method from what I've just said, or more importantly, probably ignore it because it's not going to come up on the next paper. So I'm going to place the glass block. So point 1, place the glass block on the piece of paper. Point 2, draw around the glass block. Okay, I can't make a mistake because I'm doing it in pen. Okay. So you've drawn your glass block, draw it better than mine, of course, use a ruler and so on. So first thing you're going to do, because you want to measure angles of incidences, you need to measure the angles to the normal. So the next point, draw your normal at 90 degrees to the point where you're going to shine the ray of light. And then mark out, so I'm going to use a ruler now, mark out an angle of incidence, and I'm going to start at, let's say, 10 degrees. So here's my angle of incidence here to the normal. Okay, so then you shine a ray of light using a ray box. Okay, and then obviously place your a glass block back on there. Now when you place the glass block there, you'll see, if I just turn it upside down here, you'll see a ray of light refracting, and then it will most likely emerge. So what you will do, because you can't measure the angle of refraction on the glass block, all you can do is draw the emergent ray. So if I draw the emergent ray here somewhere, now this is not completely accurate, but I'm just sort of guessing. So I'm going to draw it here. So I assume this is the emergent ray, so you're going to mark it and draw it, and then lift up the glass block and join the incident ray and the emergent ray. So then just get a ruler, join them up. Okay, make sure you draw arrows to show the direction. And here is my angle of refraction. Okay, so you've done it for 10 degrees and then repeat for 20 degrees up to 60 degrees in 10 degree intervals. Okay, in terms of anything else, in terms of safety, there's nothing to write about. In terms of repeats, the only errors here really is your reading error. So it's a random error. Human error is a random error. But because the thing's not moving, okay, that it's like no digital display, you're not reading at an angle, it's very easy to do this because the glass block is drawn on the piece of paper, isn't it? So you can't really make a mistake there. But you can say repeat for each angles, but they didn't really repeat it, so you don't have to say it. In terms of safety, nothing to talk about. And then, so this actually, now if you turn over, usually when they ask about refraction, they ask about reflection too, but we'll come to that in a minute. So then you've got this table here, so angle of refraction, degrees, angle of incidence, independent variable, dependent variable, Okay, so we sort of do that at GCSE. Student measured the angles of refraction for 2 additional angles of incidence. So the table 2 shows the additional results. So you got angles 70 and 80. So plot the results, draw the line of best fit. So just be careful here. So we're going to plot it first. So 70 and 35. So when you plot it, make sure you draw crosses. Don't draw dots. You can draw plus signs, but don't draw dots. And 80 and 37. So 80 and 37 is there. Right, so when you look at this, it's not a straight line. Okay, so at any point, that does not look straight. Okay, if it does, if you try to draw a straight line, you're going to make it look like an anomaly. All right, there is no proportionality between angle of incidence and angle of refraction. Okay, it's not in the theory anywhere. All right, so this looks like a curve. In fact, not only does it look like a curve, I could try and force it through the origin. So let's have a go, but let's just draw it freehand. So try to join them up. Okay, nice smooth curve. Don't jitter, don't hesitate, just go straight through. There you go. Okay, so there's my curve of best fit. All right, so then we've got to look at, well, why is it not proportional? So first of all, well, there's only one mark here, so it's a curve. The line curves. Okay, so it's not proportional. One doesn't increase by the same amount as the other. Okay, so there's your refraction required practical. Now we're going to come to my predicts in a minute. Obviously, right, you can just write a plan from what I've just said, or even if you drew it out yourself, if you sequenced it in your head, you should be able to write that down. Okay, but again, I'm not going to worry too much about that. So then the next part of it, you've got a figure 3 shows a diagram of a car headlight. The headlight has a lamp, reflective surface and a transparent cover. Okay, figure 4 shows a ray of light incident on the reflective surface. So complete figure 4 to show the reflected. So this is reflection. So what do we know about reflection? The angle of incidence is equal to the angle of reflection. So what we're going to do first, whenever a ray hits a boundary, we draw a normal. So draw it 90 degrees or as close as possible. So here's your angle of incidence. Now you'd have a protractor. I've done it with the protractor, so that's not exactly 90. And then we know the angle of refraction is should be equal. So we've got to sort of, now when they do this, I'll judge it by eye. So as long as it doesn't look ridiculously bad, so that's not too bad. Now if you're worried that they're not going to give you the mark, obviously get a protractor. You've got to bring a protractor to this exam because you'll need it for other questions. But just write that down also to make it obvious. And they'll just judge by eye. So that's all they'll do. Right, in terms of, right, the next question, razor light passed through a transparent cover of the headlight. So it's transparent, but it's obviously, does it tell you what material it's made of? Reflective surface, transparent cover. Transparent, so see-through, so consider it like a glass block. What would you expect it to do? It's going to do exactly what we did here. Okay, but obviously now you're just going to turn it sideways. So it's going to be this one. All right, now if you're not sure, there's your normal. This is the angle of incidence. Here's your angle of refraction. Clearly it's more dense material, so it bends to the normal. And then when it comes to this one, it's going to bend away from the normal. Okay, so it's just an example of refraction. Now this brings us on to my predicts or my analysis. So if you can see, they've done a method, a 6 marker on refraction, and obviously we've done a graph as well, plotted some points, and we've done some theory on reflection. Now if you look at 2023, they did pretty much the same again. So they've actually, if you look at it over 2023, 2022, they've done refraction to death. Okay, refraction practicals are nice methods to write, very easy, very nice sequence of events to put in order yourself. Reflection, you're not really going to do a whole practical on that, maybe aspects of it. Okay, in terms of what else has been done, you're going to see later on, we're going to look at the F equals ma, Newton's second law experiment. 2023, big 6 marker on infrared radiation. If you can't remember infrared radiation, probably because if you was in our school or in my class, we did it in chapter 2 when we did radiation, conduction, convection. We got the Leslie cubes, the cube, and we filled it with hot water, and we have different surfaces: black surface, shiny white surface, shiny silver surface, rough matte surface, etc. And we used an infrared thermometer to measure the heat coming out. So that is essentially what this experiment is. Okay, but it's not actually chapter 2, it's actually chapter 13, I think it is, which is EM radiation and whatnot. But still, they did a 6 marker on that. Okay, so if you look at it, it looks really obvious where they haven't tested. Now, the required practical on waves, there's two. There's one with the strings, a frequency generator causing loops on the string. I'll talk about that in a minute. And the ripple tag. Now, they don't lend themselves to good 6 markers. They lend themselves to calculations like V equals F lambda and working out lambda on the loops, or working out lambda using the wavefronts on the ripple tags, or from one ripple to the next. But I'll talk about that maybe on a separate video on my predicts. But as you can see, I don't expect light to come up again. I think they've butchered it. Radiation, unlikely. I mean, it came up a couple of years ago. But look what could possibly come up, or look what has not come up at all, which is surprising. But it's not surprising because it's actually a very nice plan to write. Measure the unstretched spring, measure the length of it, add a mass, measure the new length, work out the extension is new length minus original length, increase the mass by 10 grams, repeat the experiments, work out the new extension, and repeat up to 100 grams, etc. And make sure you stay within the elastic limit. And there's good things to talk about: safety, try not to exceed this elastic limit, falling springs, hit your feet, wear steel toe cap shoes, put your goggles on, make sure that clamp stand is nowhere near the edge of the table, use lighter masses, etc. F equals MA, they did calculations, evaluations, so I'm not expecting that. They could possibly do a 6 marker on that. So these 2 experiments I think you should really focus on writing your methods for, and there's loads of videos out on the internet, on YouTube, for you to look at. I don't need to really sequence it, or even just go to past papers, look at a plan and just copy that plan. Okay, copy their bullet points, make sure it's in an order that's logical and sequential. Okay, it's all right having all the facts. That'll get you a level 2 sort of response, maybe a level 3-5 marker, but to get a 6 marker, it's got to be in order. Okay, these 2 we'll have a look at, and again, have a look at it by all means. But this one, when I do my class, I basically set it up for you, so there's nothing for you to set up there. Okay, so this is what I'm thinking. I'm thinking we're looking at required practical 6 and 7 in terms of the 6 markers. Okay, graphs, F equals KE graph, force extension graph for Hooke's law, acceleration force graph for required practical 7. Again, I'll look at both of those in a separate video. Okay, so that's my sort of predicts for the required practicals. So moving on to question 2. So figure 5 shows a young child using a baby walker. So child is standing still. What is the resultant vertical force on the child? Okay, so this is chapter 8, where we're talking about resultant forces, or even if the resultant force is 0, or balanced forces, unbalanced forces, as you might remember. Now, just to revisit the theory, so you've got Newton's first law. So Newton's first law states that if the resultant force equals 0, then you could do one or two things. You can move either with constant speed, or you can be still, or stationary in this case. And then there's Newton's second law, where if there is a resultant force, that would lead to an acceleration, or rather the acceleration is proportional to the resultant force. Okay, so here you can do one or two things. You could be either speeding up, or you could slow down, acceleration, deceleration. Okay, so those are your 2 scenarios, but they've just told you it's standing still, so that must mean it's Newton's first law. Okay, so Newton's first law, resultant force is 0, or force upwards equals force downwards, or force to the left equals force to the right. But they're talking about vertical. So what is the resultant vertical force? So it's clearly 0, isn't it? Okay, the reason why, you just basically what we put down here, you could say the force upwards is equal to the force downwards. Okay, basically they're asking you to explain what does resultant force of 0 mean, so which we just talked about, or you could just talk about it here, acceleration is 0, so one of those. Okay, so that is the first bit. So just be mindful, this is chapter 8, so most of chapter 8 started off quite easy because we talked about adding forces, subtracting forces, And then it moved on to moments. Surprise, surprise. Question on moments. Okay, it looks like this is just pure chapter 8. Okay, but if you remember chapter 8 at all, if you follow the textbook, or the textbook we use in our school anyway, there's a lot of pages we've read on the outer bit. So predicts for this question or this chapter, they haven't done any vector diagrams drawn to scale and working out the results. And so again, when I do my predicts, another extra video, I'll go through some examples so you can see. But if you're not sure, I'll go through what we mean here in a minute. So use a physics equation sheet. So if you haven't realised already, this is a sheet you're going to get. It says June 2024. I think 2025 is the same. So these are all paper 1 formulas, and paper 1 ends here on PV or P1V1 equals P2V2. So the rest of these are your paper 2 formulas. Now, you probably notice work done is here. Work done is force times distance, and that's what this one's about. Now, work done is force times distance actually came up in chapter 1 of the textbook, didn't it? So, because it's part of the energy equations. So just be mindful, you've got to be prepared to use it here, which clearly we have to. So write down the equation which links work done equals Fs. So I'm just going to write down in symbol. So work done equals Fs. Okay, so they tell you, I don't need to look at the picture, I don't think. So the child pushes the baby walker a distance of this, so there's my S, and the work done is equal to that. Sometimes I'll leave it as WD. You don't have to, you can leave it as W. But if you leave it as W, sometimes people confuse that with weight. Okay, so maybe I will just put work done equals Fs. So calculate the horizontal force. So they're asking for F, question mark. Okay, so right there, now look at the units. Meters is fine, joules is fine. There's no kilos in front, there's no anything. Okay, if you've forgotten them, they're all here. Okay, so calculate the horizontal force. So write out your formula first, that's the least you can do. And then you should be able to then put the numbers in. So 35 is equal to F times 2.8, and then we want to get F on its own, so move the 2.8 over, it's multiplying, so divide, so 35 over 2.8 is equal to F, and if you work that out, that should give you 12.5 newtons. Okay, so nice and simple. Now obviously that seems far too simple for a higher paper, so they're going to ask you something about the formula, or maybe just some what ifs. So let's just move this out the way. Right, so the child pushes the baby walker from a carpet onto a hard floor. So what do you know about a hard floor compared to a carpet? There's clearly less friction, isn't it? It's smoother. Okay, so these are the things you should be going through your head. And you're probably thinking, well, where's this in the physics textbook? It's not, it's common sense. Okay, most of physics is common sense. So explain why the speed of the baby walker increased. So if the speed increased, we're now thinking about Newton's second law. Okay, so now if you think of the walker, now what we've got to be able to do, you've got to get a picture like that and turn it into a free body diagram. Now what is a free body diagram? Basically, don't draw the object, just represent it as a particle. Okay, so the baby pushed the walker. So if you got the force from the push, okay, so FP from the push, and you got force from the friction, which we normally call FR. Well, if your speed is increased, you're accelerating. That means you got a resultant force. That means one force is bigger than the other, and you accelerate in the direction of the biggest force. Think of tug of war. So that must mean the frictional force this way, FR, or rather FP is bigger than FR, or the resultant force is equal to FP minus FR, the force of the push minus the frictional force. Okay, so the child applied the same horizontal force. So explain why. So we pretty much answered it there. So if you look at what we wrote here, you say frictional force decreased, went down, or you could say what we just said here. There's a resultant force forwards. Okay, and that has now increased. So that caused the acceleration. All right, so that is the again, free body diagrams hasn't come up. They haven't asked you to draw one yet, so maybe they could. Okay, it's very simple. Whatever the particle is or whatever, just turn it into a point particle and just draw the forces on it, free of any illustrations and and whatnot. Okay, that's not the literal definition of it. That's just me trying to get it in your head. Right, so now we've got this gear question. Now these don't come up often. Okay, now you're probably thinking, well, what's the science behind gears? Well, it's not really a science. If you look at it, it's actually linked to moments. So what you've got a force causing a rotation, whether it's clockwise or anti-clockwise. So you've got a force here. So clearly this is your pivot. Okay, now what is the equation that links distance, force and moments? So if you go back to here, moments is force times distance. So at moments, capital M is equal to FD. Okay, so the child applies a force of this. So there's your F. And the perpendicular distance between the force and the pivot is 7.5 centimeters. Notice 3 marks for such a simple formula. Units, so clearly we've got to change those. So there's your first mark, so 0.075 meters. So there's your first mark. Okay, calculate the moments. So put it in the formula. M is equal to FD. Substitute it all in. So substitute first before we have to rearrange. We don't have to rearrange here. So 2 times 0.075. Okay, put it all into your calculator. So I get 0.15 Newton meters. Okay, and Newton meters are here anyway. Right, so if you look at it, this is going to cause about the pivot, this cog to rotate this way. All right, so explain what happens to gear B when the child applies the force to gear A. So if this one goes anti-clockwise, what does it do to this one? It causes this one to move clockwise. So if you're not sure what to write down, because it does say explanation, so I get that, at least state the obvious. So here, just say gear B rotates clockwise. So start off with what you do know, state your obvious stuff, and then maybe we could piece something together. Well, gear B rotates clockwise and gear B is smaller. So gear B will be rotating faster. So gear B rotates faster. Now, I'll explain that in a minute. Now, why is it gear B is rotating in the first place? Is because the moments created by the 2 newtons force has been exerted onto gear B. Okay, and that's simply it. So you could say one or two things. Gear A now exerts a force on gear B, or gear A causes a moment onto gear B. So gear A exerts a force or a moment, so you could say either, because a moment is a force times the distance, on gear B. So that's your explanation. The top bit is your stating the obvious, so get the stating the obvious stuff, that's the easy bits, and then focus on, well, what's caused it then? Let me think. Oh yeah, gear A is pushing gear B. What's another word for push? Well, push is a force, isn't it? Okay, so that's the sort of things you got to think of. Now, let's go to my predicts. I will go this in a bit more detail later. So what do I predict from chapter 8? Okay, so what have they not talked about? Right, so first of all, vector diagrams. So if you've got 2 forces, let's call it A and B. And where is the resultant force? And they usually ask you to draw a scale diagram. First of all, we know it's here somewhere, but you got to draw it to scale. So if I said to you A was 60 newtons and B was, let's say, 70 newtons, what have you got to do? You got to draw a scale first, haven't you? So here, it's nice and easy. I would say 1 centimeter is 10 newtons. Okay, and then you got to draw it to scale. Now, what they encourage you to do at GCSE, now you've been told 2 methods. The one I prefer is not the one they would expect you to do. If you look in chapter 8, the textbook itself, there is actually a page called parallelogram of forces. So they expect you to draw a parallelogram. So this one's quite straightforward because there's no sort of angle other than 90 degrees here. So mimic it. So draw this 6 centimeters long, draw this 7 centimeters long, and then draw your parallelogram, so the parallel sides to that. Make sure you draw arrows because they are vectors. Okay, now the question is, where's the resultant? Well, from the start to the end. Use your common sense. You're clearly not going, if you're pushing to the right and you're pushing down, you're not going to go up and to the left. You're going to go to the right and down. Okay, and then measure that What it's clearly, I mean, you could argue, well, I'm going to do it by Pythagoras. Yes, you can, but that's not what they're asking. They'll ask you to do by scale diagram because it's a vector. Not only would they want you to work this out, let's say this was 8 centimeters. I'm no idea. So 8 centimeters, which is 80 newtons. Not only do they want that, they'd want an angle. So whether you give it to the vertical or whether you give it to the horizontal. Okay. If you give that angle, now you're probably thinking, how am I going to do that? Do I have to use trigonometry? No. Use a protractor. It's by scale diagram. It's not by calculation at all. Okay. And then use a protractor and make sure you say if I give this one, I would say 80 newtons at 20 degrees to the horizontal, or I'd say 30 degrees to the vertical. Make sure you refer to that, or make it obvious in your picture which one you've actually pointed out. Okay, so from chapter 8, this hasn't come up from what I've gathered for at least a couple of years. Okay, so expect to draw a vector diagram of some sort. Okay, what I will do in the video, like I said, I'm going to go through my predicts. I'm also going to go through all the higher stuff on from the textbook in terms of examples and theories. So just look out for that in the future. So let's move on to the next question. Okay, so question 3. So this one looks like a spacey question. So this is chapter 16. So chapter 16, solar system, life cycle of stars, expanding universe, okay, and the eventual fate of the universe. So if you look here, universe contains many stars. Sun is a star at the center of our solar system. Give 3 other types of objects from our solar system. So this is basically asking you what does the solar system contain, which is really straightforward. So planets, obvious thing. So that's the first thing that springs to mind. Now, other things, I mean, there's dwarf planets as well. I say dwarf planets, there's only one, as Pluto has been downgraded for some reason. You got moons or natural satellites. Okay, now you can't mention artificial satellites because they're not in all other systems, because they're clearly things we've put up in the sky, night sky. Then you've also got things like asteroids, you could probably say, and the other one, really important, comets, because they have very oval shaped orbits compared to planets which have more circular shaped. Okay, so those are sort of things we could talk about. So some main sequence stars will eventually form black holes. Now, I will answer this, but I'm going to talk about what they haven't talked about yet, okay, for a couple of years now. So some main sequence stars will eventually form black holes. Okay, so you got 4 stars here, gives the masses of them. Which star in 3 is most likely to form a black hole? Okay, so you would only form a black hole if your mass is at least 10 times greater than the mass of our sun. Okay, so it's going to be massive or much more massive, and that's the sort of rough ballpark for you. Okay, and we'll talk about what main sequence means in a minute. So if you look here, this is times 10 to the 30. Well, the sun is times 10 to the 30. This is times 10 to the 30. That's similar masses. Arcturus is times 10 to the 30. Similar masses. So these 3, their eventual fate, as you know, is going to, once they stop becoming the main sequence, they'll become a red giant. And once they stop fusing anything, because what happens, we'll talk about it in a second. So this will then become a white dwarf, and that will eventually become a black dwarf. Okay, so that's your basic theory for those. Betelgeuse or Betelgeuse or Jace, whatever, is clearly 31, so it's a factor of 10 times bigger. So the answer here is Betelgeuse. Okay, so things to remember, and then what they haven't asked about, we're going to look a little bit later on. They haven't asked about main sequence stars in detail. So you'll see what I mean in a minute. So the distance from Cygni A to the Earth is 1.1 times 10 to the 8 gigameters. So giga times 10 to the 9. So what distance is the same as 1.1 times 10 to the 8 gigameters? So what they're telling you there is 1.1 times 10 to the 8 and another 10 to the 9. So 8 plus 9 is 17. So it's that one there. So make sure you remember your prefixes. So now, if we turn over really quickly, the reason why I say this is this thing here about hydrogen and so on. So what I'm going to do, just quickly go over what happens in the life cycle of a star. Okay, so let me just grab a piece of paper. And again, it's all just loads and loads of facts. So you start off with your cloud of dust and gas, or your nebula, okay, which is your cloud of dust and gas. Okay, when we say cloud, we're talking huge amounts of matter, something you probably couldn't comprehend on our scale, much larger than the solar system. And what happens? Gravity or gravitational forces pull these together. What does that mean? You've got intense heat. So you've got what we call a protostar. Okay, so here you have got intense heat and pressure, but insufficient for fusion. Okay, so what do we need? We need to pour more. Gravity needs to work again to pour more cloud of dust and gas. So eventually it's hot enough for fusion to occur. So yeah, this is what we call main sequence star. Okay, and main sequence, you have fusion, and they have the fusion, and if you remember it was H21 plus H31 is equal to helium-4 Okay, so clearly the top numbers don't add up or balance, so there's missing mass, and that missing mass turns to energy. So why is it called the main sequence star? Here, the fusion pressure outwards is balanced by the gravitational pull inwards. Okay, so you've got the gravitational pull inwards. Okay, so that's what they haven't asked about yet. Okay, so they could ask you about how does it become a main sequence star, or what forces are involved, or why is it a main sequence, what's balanced there. Okay, eventually, if the once you're a main sequence star, or you come to the end of your life, depending on your masses, so if you're close to the mass of the sun, approximately, then what you'll become a red giant. Okay, here you have fusion of helium into heavier elements. Okay, all the way up to iron, or Fe. And then once that stops, then you become a white dwarf and a black dwarf. Okay, so that's your basics for what's going to happen to us. All right, now this has come up last year. Okay, so if I can recall, it didn't come up last year, it came up in 2022. Life cycle of both large small stars like ours, and also large stars. Now, if you're at least 10 times the mass of the sun, you are going to become a super red giant. Okay, and here you have fusion of helium into heavier elements, all the way up to iron again. But what happens here? It's supernovae, so it explodes. Intense heat, intense pressure causes fusion of Fe into heavier elements. Okay, for example, all the other elements in the periodic table above it, iron. So if you think about it, if you've got suns dying like ours, they will eventually just produce iron. So iron is actually one of the most abundant elements in the universe because it's dead stars. But if they are huge, massive stars, they will super red giant, supernovae, and that's when they'll produce these other elements: gold, aluminium, everything, uranium, plutonium, all of the elements in the periodic table are formed there. So if you think about it, the fact that we have heavy elements in Earth means we were probably remnants of a supernova. Okay, so hence this life cycle. That's why they call it life cycle. And obviously, if you're very heavy, you'll become a neutron star, and if you're ultra dense, you'll become a black hole. Okay, so those are the fates, and those are the processes. So that's a nice little thing to remember. Okay, in terms of what you need to be able to churn out, even if 6 markers either way. Okay, and also talk about the forces, the processes involved. Okay, so let me find my red pen. Okay, let's move on then. Let's see what the rest of this question is about. So you've got what looks like light from spectrum from every galaxy includes dark lines. Lines have the same pattern. Figure 7 shows the position of dark lines in the visible spectra of lights from the sun and from 2 distant galaxies. Explain what these light spectra tell us about the velocities of galaxy A and B. So straight away, you can see these lines have been shifted towards the red. Okay, so state the obvious first. So both galaxy A and B are moving away because they're redshifted. Okay, so that's the obvious thing. They're both moving away. But clearly, galaxy A, if you compare these lines here and that one, galaxy A has redshifted more. So galaxy A has a greater redshift. So all I'm doing is just stating the obvious first, greater redshift. And what do we remember? The greater the redshift, the further away you are. The further away you are, the faster you are moving, because the distance between you has increased, the gravitational force between you, the force of attraction, is weaker, so you can zoom off at a faster speed. So galaxy A has greater redshift, so it means it's further away. But that's not what they're asking. They're asking about the velocities. So galaxy A is moving faster away. Okay, so that's essentially, that's all they can probably ask you about redshift. And then they'll ask you, well, what does it tell you about the universe? Everything is moving away from each other. Everything is expanding away from each other, so therefore the universe is expanding. And then they might ask you, what is the origin? You know, what does this evidence lead us towards? Well, sometime in the past, we weren't moving away from each other. We must have been closer and closer together. Eventually, we was one single point, and then maybe the Big Bang caused us to explode and move into all other directions. Then they could ask you what other evidence was there of the Big Bang. So you say CMB, or cosmic microwave background radiation, which is like an afterglow of the explosion. Okay, and it's all around us. It's everywhere. Okay, so we're detecting in all directions, so that must mean it came with the expansion, possibly. Right, so now let's move on to the next bit. So we've got this distance between Arcturus and the Earth is 3.6 times 10 to the 24 kilometers. So kilometers straight away. We've got to be careful there. So that now becomes, well, kilometers, if you look here, kilo times 10 to the 3. So times 10 to the 3 added on to 10 to the 14, so that becomes 3.6 times 10 to the 17 meters. So that's your distance. They've given you the speed and they want the time. So what formula connects those? If you look here, S equals VT. So I'll just use that. S equals VT. Clearly I've got the first mark for the conversion. So expect a lot of unit conversions. Okay, so I'll put the numbers in first. So 3.6 times 10 to the 17 equals 3 times 10 to the 8 times by t. They just go rearrange for that. So t is 3.6 times 10 to the 17 over 3 times 10 to the 8. Put it all into your calculator. So my calculator gives me standard form, which is fine. So 1.2 times 10 to the 9 seconds. Okay, so there's your final answer. Right, so the last bit is the bit what we was talking about. When stars are formed, they contain mostly hydrogen. Hydrogen turns into helium during fusion. Fusion requires high temperatures, high pressures. Easily done in a star because it's really hot and a huge gravitational pull pulling the masses inwards. So when stars are formed, they contain most hydrogen. Describe how stars produce all other naturally occurring elements. Okay, so what do we know? So fusion occurs in main sequence stars. So just write down everything you know, and you probably answered it. In fact, we've probably answered it in what I said earlier, making sequence stars. So hydrogen fuses into helium, and then during when stars, so let's use the normal star, like a star same size as ours. So during the red giant phase, you get the fusion of helium into heavier elements up to iron. Okay, and then during a supernova, so let's put super red giants as well because that happens there. Supernova, you get the fusion of iron into heavier elements, and these get spit out all into the universe, and somehow some of them cool down and form planets like ours. Okay, so that is chapter 16. What have they not talked about? They haven't talked about how you become a main sequence star, the forces involved in terms of, they've talked about redshift. They talked about redshift last year as well, and they didn't talk about Big Bang Theory last year, but they talked about it 2 years ago. So life cycle, I think they've killed it, to be honest. But again, they're nice sequences. Just remember these. Put these into your own words if you can. In fact, if you drew it like that, I don't see why you won't get the marks anyway. It's not an English exam. They haven't talked about the fate of the universe. One thing they have not talked about, it's the only higher thing on this chapter, is orbits, circular motion and orbits. Okay, centripetal force, gravitational force acts as a centripetal force pulling towards the center. Therefore, the force is right angles to the speed. Therefore, it goes around the circle. And again, I'll talk about that in another predict video. So that's the end of question 3. Okay, moving on to question 4. So Mariana Trench is the deepest part of the ocean. Figure 8 shows a submarine going to the bottom of the Mariana Trench. Okay, so this looks like depth of the submarine increases. Explain what happens to the pressure. So this is chapter 11. So this is water pressure. So as we know, pressure increases this way. Increases, but as you go upwards, pressure decreases. So the answers are sort of similar, or the explanations. Pressure decreases, my fault. This way. Okay, so why does the pressure increase as you go further down? Simply because of the weight of all the water above you. Okay, so there's more particles hitting you. Why does the pressure decrease as you go further up? Air gets thinner, less particles, less collisions of air particles on you, less pressure. Okay, and because pressure equals force over area. Okay, so in terms of what do we write there, you just literally write down what we just said. So talk about, for example, the water, larger amounts of water above you. Above the submarine in this case. So think of a pylon when you jump on top of each other, everyone jumps on top. Well, who feels the most pressure? Clearly the person at the bottom, because of the weight of all the large amounts of water above. So greater weight acting on the submarine. And it is as common sense as that answer. Okay, so that's what you got to look out for. So what do we know anyway? Pressure in water, pressure with depth, that's H. You've got this formula, pressure equals rho GH, which is pretty much what we're going to use there. Okay, so submarine moved from the surface of the water to the bottom of the Mariana Trench. So go all the way down there. Change in pressure was 110,000 kilopascals. Kilo, so we've got an issue already. That kilo is times 10 to the 3, and in this case I'm just going to add 3 zeros, so 110,000 pascals. Okay, so there's my first mark. That's what it's for. They give me the density, so I've got the pressure. They give me G, and they're going to ask me for H. Okay, so clearly expect to rearrange formulas, but if you're not very good at rearranging formulas, so pressure is rho GH, which is here, or H rho G as they call it. Rho GH just rolls off the tongue better. So pressure I've got is 110 million. So I'm going to get another mark here just by putting all the numbers in, times 9.8 times H. All right, so then just rearrange. If you want to neaten up this first, you can do. It's up to you. I'm just going to quickly zoom through it. Over 1026 times 9.8. Okay, so if I put the numbers in, okay, units are all correct, so I've got no issue with that. Okay, so that will give me 10,940 meters. Okay, so nice easy starter. Now what could they do to make this harder? Okay, so if I just get another paper and show you, how can they make this harder? So if, let's say for example, because I've just mentioned pressure, and the first thing that comes to your head when you think of pressure is force over area, which it should as well. So if a classic question came a couple of years ago, if you got a brick and it's underwater, could you work out the force? And if I gave you this area, let's say that's 0.5 meters by 0.2 meters, could you work out the force exerted on there? If I gave you the density is 1,000, just normal water, and this height to here was 3 meters, and we know G is 9.8. Okay, so how do you work out force? Well, what can we work out? We've got H, we've got rho, we've got G, so we can work out pressure equals rho GH, but I'm trying to work out force, and I've given you some dimensions which you could work out area, so that will equal F over A. So just be mindful, this is where they could go next, and they haven't gone that way last year, but they did go that way in 2022, because that's the only way to make this harder. All right, and I think it was a 5 marker. In fact, it was a swimming brick a brick in a swimming pool. What's the force exerted? It could be anything. It could be a treasure chest. What's the force exerted on the lid of the treasure chest? So just be mindful of that. Sort of predicts what could come up. And again, I'll try and go through some questions or examples for you. So now they've gone off water pressure and they've gone on to earthquakes. So earthquakes, P waves, S waves. What do you know about P waves? Let's just write down what you should know before I even answer this. S waves. S waves, S transverse. They are the slower ones. Okay, and they only travel in solids. Okay, so that's your S waves. So P waves must be the others, so that's longitudinal. Okay, therefore it must be the faster of the two. P waves arrive first, S waves arrive later, and it goes through solids and liquids. Okay, so that's your basics. You should know that without even reading the question. So which statement describes P waves and S waves? So clearly, just from recalling your facts, which you should be able to do really quickly, P waves are longitudinal, S waves transverse, so it's there. Okay, so question 4.4. Figure 9 shows the layers inside the earth. An earthquake occurs at position A. Position shown. What do we know? So solid mantle core, solid liquid outer core, solid inner core. So which letter shows a position where only P waves will be detected? Okay, so P waves is good. If you think about it, if you've got a liquid core, then you're not going to get any S waves traveling through there. So therefore, there's not going to be S waves here. So here is what we call a shadow zone or an S shadow zone. Okay, so the only thing you'll receive here, P waves. Here, A, B, C, you're very likely to receive P and S waves, but I'm going to talk about that in a minute. So first of all is D and Y, only P waves travel in liquids or liquid outer core. Now, what they've done, this is not normally how they ask the question. They ask the question the opposite way around. They normally ask, there's a shadow zone here where you've not detected any S waves. What does that tell you about the inner core or the core? So this is where you say if there's no shadow, if it's the shadows or no S rays, that must mean part of the core is liquid, the outer core is liquid, the inner core is solid. Right. So what happens as it gets to here? Okay, it's the P waves will pass through, and then it'll come to here. Now, the S waves will come here, but they'll stop. But you'll receive S waves here and P waves, and you'll receive S waves and P waves here. Notice I've drawn the lines curved because there's a change in direction. Now, what is another term for change in direction of a wave? Refraction. So the question is, why are these lines refracting? Because there's a change in density. Why is there a change in density? Is because it's getting hotter, it's becoming more molten, so it's becoming more like a liquid than a solid. So clearly there's a change in the speed in there. Now, if you remember refraction, well, actually, we'll leave that. That's all you need to know for this. So this is all the theory of P waves and S waves. Now, from what I gathered, they didn't come up last year. Sorry, they didn't come up in 2023. They've come in 2024. Am I expecting them to do this again? Well, what they haven't done from this chapter on waves, on S waves, P waves, they haven't done speed of sound, uses of ultrasound depth testing, measuring distances or echoes and dividing by 2 to get the distance or the depth. So they haven't done that yet. Okay, so let's have a look at this bit here then. So an S wave has a frequency of, so there's your frequency. S wave has speed of, so this is your speed, but it's not your speed, it's in kilometers, so it's equal to 4.5, so that's 4,500 meters per second. So I'm going to get a mark for my conversion already. Calculate the wavelength lambda. So what formula connects all those three? So you should realize it is V equals F lambda. Okay, so anything to do with waves, wave speed. So V equals F lambda. Okay, so we're trying to work out lambda. I'm going to put the numbers in first. So 4,500 is equal to F, which is F times lambda. Sorry, I meant to put the numbers in there. So 3.6 times lambda is 4,500. So lambda is 4,500 over 3.6. So it's in the calculator. Let me see what I get. So that would be 1250 meters, 1,250 meters. So again, nice, easy. Just remember conversions, unit conversions. Keep looking out for them, please. So a seismometer or seismometer, how are you going to pronounce it, is a device that detects earthquakes. P waves travel at known speed between an earthquake and a seismometer. S waves travel at a slower speed than P waves. Yes, that's what I mentioned earlier. P wave and S wave from an earthquake arrive at a seismometer at different times. Describe the relationship between the distance from the earthquake to the seismometer and the time between the P waves and S waves arriving. Clearly, if the distance goes up, the time's going to increase, and the time between the P wave and the S wave is going to increase too. So common sense tells you, because we're just using speed is distance over time, or distance is speed times time, they're proportional. So distance is proportional to time between P and S waves arriving. Okay, so clearly if there's a bigger distance, the time between receiving the first one and the second one is going to get bigger because they're traveling at slower speeds. So slower speeds, then that means more time in between. So that is, and again, we're expecting questions on measuring the speed of sound, ultrasound, uses of ultrasound. So that could be what could possibly come up on chapter 12. Okay. Okay, let's move on to question 5. So question 5 looks like a required practical. So if I just go back to these. Okay, so we're on to this bit here, calculations, evaluation. So they haven't asked you for a procedure for this one, or a 6 marker, or Hooke's law. So like I said, these are two I think you should focus on for your 6 markers. In terms of reflection, refraction, which is chapter 12, that comes up a lot. Okay, now, just one of my predicts, for chapter 12, we've got now reflection and refraction. What we haven't got is the theory on wavefronts, and more importantly, what hasn't come up is ray diagrams. So ray diagrams for convex lenses, more specifically, but also even how to draw the parallel rays entering a concave lens. So during my predict video, which I'll probably try and do after this, I'm going to just go through all the examples that you need to, and then you just got to keep practicing. Okay, so prepare for things. In fact, ray diagrams haven't come up for 3 years, so just bear that in mind. So let's look at this one here. So question 5, student investigated how the acceleration varies with force. Now we already know this is Newton's second law, don't we? So Newton's second law, acceleration is proportional to force. What formula is it? F equals ma. So if you're testing the relation between F and m, what must be constant? This must be your control variable, isn't it? All right, so what is the name given to the force F? So force F, what is the force in the string that's keeping it tense? Well, it's the same force there. We call it the tension, don't we? So tension in the string. Okay, there's no other word for you to use there, so you need to remember any forces in a string, in a rope, in a chain, in any sort of like thing that can stretch, even a spring, is tension. Okay, so give one variable that should have been a control variable. So here, now what is it that's got to stay the same? It's not just the mass of the trolley, it's the mass of the trolley plus the mass of the hanger. So mass of trolley plus hanger. Now you're probably thinking, why? Because both of these are accelerating. As this moves that way, this is clearly moving down, isn't it? So both of these accelerating, and you've got to keep them both. So the best way to explain it, if you had lots of masses here, if you take one of the masses off here, you have to put it on there, because you've got to keep the mass of the whole system constant. Okay, so just be mindful of that. Will they ask that again? Well, they've just asked it in 2024. They're not going to ask it in 2025. Okay, but they might ask you for a method. What would you do? What can you do? Well, it starts at 0, so u equals 0. You add a mass, measure the distance, measure the time taken to go from there to there, so you can work out the final velocity. Here, you know the initial velocity, so you know v, you know u, you know the time it took, so you can work out a. So you know the A. Now you know the mass of the slotted masses, because there'll be 100 gram marked on there. From the masses, you've got to work out the force. Okay, F equals, because it's the weight, here the force is equal to the weight, which is equal to mg. Okay, and make sure you turn the mass has got to be in kilograms. Okay, and again, in my predict video in a bit later, I'll go over that practical in detail, or just watch a couple of YouTube videos, or watch mine so I'll get more hits. Okay, so now let's move on. So I've pretty much answered this now, haven't I? So student held the trolley stationary, so u equals 0, released it, moved with constant acceleration. There is only one formula for constant acceleration that you should be focusing on: v squared equals u squared plus 2as. Okay, now this brings me on to something we need to talk about later. Which acceleration formula do we use? I'll come back to that in a minute when we get to the end of this. So student recorded the time taken. So if you know the time and you know the distance, what formula connects these? You can work out the speed, can't you? Speed is distance over time. So that's your final velocity, your initial velocity, you've got the time. So what have you got? You've got u equals 0. You can calculate v, which is s over t. So you got these two. You got the time clearly, okay, and you from these you can work out the acceleration, okay, because acceleration is v minus u over t. Okay, if you know that, and we also know the s, okay, we've got quite a few things there. So describe how the acceleration can be calculated. So you could argue, let me use v equals u plus a equals v minus u over t, or I would just go to this one. So you've got all this information, so this will be part of the answer, and then I would say you would use v squared equals u squared plus 2as. U is 0, so v squared equals 2as. So you need to know the distance. You can work out the final velocity using v is equal to s over t. Therefore v squared is equal to s over t squared. Okay, so you can put that in there also. So that is where the marks are. It's really just, I mean, if you just wrote it like that, that's plenty. So for one set of results, the force acting through the string was 2 newtons. The student released the trolley 3 times. They determined the following values for acceleration. So you got 3 values. You can work out the average. Okay, in this case, it's quite easy because this looks like the mean. So it looks like 1.36, or call it the mean if you want. Calculate the uncertainty in the values of acceleration. Now, if you get what's called a data set, a set of data, to work out the uncertainty is simply the range divided by 2. So in this case, well, what's the range? The maximum is 1.39 and the minimum is 1.33. So the range is 0.06. And then divide that by 2. So that gives you plus or minus 0.03. Now, the uncertainty, you could have got another way. You could have just said, well, if 1.36 is the average, what's my 2 extremes? My upper extreme is 1.39, so I've gone up plus 0.03, and my minimum extreme is 1.33, so it's gone down by 0.033. So if you think about your answer, it's 1.36 plus or minus 0.03. So that will give you 1.39, and that will give you 1.33. It's just out of chance. It's quite easy to do in my head. But if I gave you 3 numbers, 1.74, 1.71, 1.75. So I don't know. I'm just guessing. I'm just sort of make these up. So let's work out the mean and work out the uncertainty. You work out so 1.74 plus 1.71 plus 1.75 equals. So that gives you 5.2. Divide by 3. So your average is 1.73 recurring, but I'll leave the recurring for the time being. Now work out the range. So the range is, well, 1.71, so that's 0.04 over 2 is your uncertainty. Okay, so in this case it's plus or minus 0.02. So that's how you work it out. So you can do it with any set of data. If you've got a data set, it doesn't come up often, these uncertainty things. Usually they just ask about resolution and stuff like that. Right, so now let's move on to the last bit, the what ifs. Okay, so components, the runway was then raised at one end. Force acting through the string remained the same. Explain how the acceleration was affected by raising the end of the runway. So first of all, what you're going to notice, clearly it's going to go faster. So just say the acceleration increases or gets bigger or is greater. So just get your first mark. Now let's think about, well, why is your acceleration greater? Okay, now you could do this using what you remember from chapter 1, energies. You've now increased the GPE of the trolley compared to here. So it's got more GPE, and that GPE is going to be converted to kinetic energy. So it's going to have a higher velocity, therefore it's going to have a bigger acceleration. So we could say that. You could say GPE increases, and that gets converted to KE. So that must mean larger final velocity, which means greater acceleration is larger. Or you could talk about it in terms of forces. So you could say, well, I mean, this is the tricky bit. Clearly, part of the weight of the trolley is acting down the slope now. Okay, so therefore so you could say a component of the weight of the trolley acts in direction of the motion. Okay, so this one's a bit more complicated. It is the last part of the question, so you've got to expect some sort of difficulty. But even just take the obvious first, take what you do know, and then work it out from there. Now, going back to this acceleration, which one do you use? So you've got 3 formulas. You've got A is equal to V minus U over T. You've got F equals MA. And you've got V squared equals U squared plus 2AS. Which one do you use? Use this one if you've got the time. Use this one if they give you the mass or the force. Use this one if they give you the distance. Okay, so that's the way you got to sort of judge which ones to use. If not, just write them all down and see what you can use. Okay, something will pop up. Okay. Okay, moving on to question 6. So this is your chapter 13, electromagnetic waves, uses of waves, dangers of waves, properties of EM waves, and so on. So so radio waves and gamma waves both transfer energy. That's the definition of a wave. They transfer energy, information, but they don't transfer matter. Give 3 other similarities between radio waves and gamma rays. So first of all, they're both electromagnetic waves. Okay, so because they're part of the EM spectrum, that's what chapter 13 is about. And what do we know about all EM waves? They travel at speed of light. Okay, and they travel in a vacuum. Okay, and also the thing, because they're EM waves, they're transverse waves. So those are your basics, really. Make sure you know the uses, properties of all the waves. Make sure you know the order. Okay. And then what is it? I mean, this chapter is dead easy. If you remember, you pretty much covered it in a couple of weeks, or a couple of lessons rather. So both radio waves and gamma rays are used in medicine. Okay, so it's basically the best way to explain it. There's not much that is higher tier in this. There's probably how we produce radio waves. Okay, but besides that, there's not much else. So what can they do to make it difficult? They're going to ask you to elaborate on one of the uses. So give one use of medical, give one medical use of gamma rays. So gamma rays, if you didn't remember, it's used for radiotherapy, so treating cancer. Okay, you could also say it's used for sterilizing medical equipment. Okay, because it's very effective in killing bacteria or germs because it's high frequency, high energy. Right, so anything else? You could have said like medical imaging. So we talked about radioactive tracers, PET scans, gamma cameras, which not really covered on the spec, but some people know about it. But don't worry if you don't, just stick to the ones we do talk about. Okay, so explain why exposure to gamma rays can be harmful, but exposure to radio waves is not harmful. So if you remember, gamma rays and X-rays are both ionizing. Okay, everything else are not so. Okay, so we can write that down. So gamma is ion. Now you're probably thinking, yeah, that was chapter 7, alpha, beta, gamma. Yes, but then if you remember, I said, well, gamma is weakly ionizing. I know it's weakly ionizing, but it's still ionizing. So what could it do? It could mutate cells, the DNA. Okay, so that could lead to cancer. So this is an explanation. That the first sentence is just a statement, a lead to cancer. Okay, or you can give the opposite argument. Radio waves are not ionizing, won't cause any damage, and so on. Okay, so then here we go. So this is the only higher bit, or one of the few higher bits on chapter 13. The other one is uses of X-rays. So I'm expecting uses of X-rays, how X-rays are produced, images of X-rays are produced. That's going to be the sort of question that could come up on this. And also don't forget, because it's waves, they can use V equals F lambda as a calculation also, so expect that. So some medical scanners produce radio waves at specific frequencies. Explain how radio waves are produced at a specific frequency. So basically they're asking you, how do you produce radio waves? So what you do, you start off with, so the best way to explain, let me just draw it. So you've got something here that produces, it's basically a power supply, and that produces AC, so AC current. And what this current does, it travels up and down this wire because it's constantly changing direction. So this is what we call the transmitter. And let's say the AC current's at a particular frequency. I'll just use 50 hertz because that's what you're used to. So that means these electrons are going up and down here from the power supply at a frequency of 50 hertz. Now what that does, try and follow my pen, as it goes up and down these electrons, it causes a radio wave to come out. And this radio wave is, coincidentally, 50 hertz. Now what you have at the other end is a receiver or an aerial, which looks exactly like a transmitter, and as these radio waves come here, they cause the electrons in the wire to oscillate just like the waves do, and surprise surprise, this produces, so if you've got a cathode ray oscilloscope, you'll see a radio alternating currents here. So you get an AC current. Coincidentally, the AC current here is 50 hertz. Okay, so that's basically how you produce radio waves, because it's alternating currents or oscillating electrons being transmitting radio waves. So let's put this into words somehow. Oscillations produced from AC circuit produces waves of the same frequency of the AC circuit, and that's it. That's all you need to put down here. No reference to receiving and so on. Will this come up next time? I doubt it. They've already asked the X-rays, uses of X-rays, dangers of X-rays, which is quite a meaty question they could ask. So moving on to question 7. So this is your motion graphs. So motion graphs, if I remember, was chapter 9. So figure 12 shows a velocity time graph for a train travelling between two stations. So it's a VT graph, so two things you need to know. Gradient is the acceleration, and the area is the displacement or distance. Okay, so if you look here, what have we got? We've got constant gradients, so constant acceleration, zero gradients, zero acceleration, so it's moving at constant speed, and then you've got a constant gradient, got a constant acceleration, but now it's decelerating, so you've got a constant deceleration. And here you've got another constant gradient, so you've got another constant acceleration or constant deceleration. What do you know about this one? This one is a greater deceleration compared to this one. Okay, and so don't forget, if there's a, how do you now link this to forces? Here, acceleration, so you've got a resultant force. Because here you've got a resultant force of 0, because this one's Newton's second law, this one's Newton's first law. Here you've got a resultant force, this is Newton's second law. Here you've got a resultant force, Newton's second law. But this resultant force is bigger than this resultant force, because this acceleration is bigger, because F equals ma. And so therefore the acceleration is proportional to the force. So bigger acceleration or bigger deceleration, bigger force. Okay, so that's what you should be able to decipher straight away. So no questions need to be asked. You need to do that. Okay, determine the distance travelled by the train in the first 600. So distance is area, 600 seconds. So what you can do, I would probably split into a triangle. Okay, and a rectangle here. You could do trapezium method if you want, it's up to you. Nothing's stopping you. So distance equals the area of the triangle plus the area of the rectangle. So that's a half times the base, which in this case is 220, times 56. That's the triangle, plus base times height. So 220 to 600, so that's 380. Base times height, which is 56 again. Okay, so let me just put that in. So 6160 plus 21280. Okay, you don't have to put the middle step, you just put it all in if you want, it's no problem with that. 27,440 meters. Okay, so that's your basics. What else could they ask you to do on this? They could ask you to calculate gradients. Surprise, surprise. Look at the next page. Explain what happens to the braking force as the train decelerates. Okay, so what do you notice? But what I'll do, as it starts to decelerate, I'll split into two. So always, if you get changes in gradients, describe each gradient separately. So between 600 to what looks like 720, large gradient, so large deceleration, so that must mean large braking force. Now you're probably thinking, what formula have I used here? I've just used that. That's what this is about. That's the only other theory here. Okay, now look from 720 to, what's that, 960. Okay, what do I notice? Small gradients, so that means small deceleration, so that must mean a small braking force, or even the resultant force is smaller. Okay, so there's my 3 marks, and all I've done, just state the obvious stuff. Okay, so determine the maximum deceleration. So clearly that's happening between 600 and 720 seconds. All right, so how do you work out that? It's just basically this triangle here. So we know what that is. That's 20 to 56, that's 36. Okay, and that is 120. Now, if you do, you could actually just do deceleration. A is v minus u over t. So v is 20 minus 56 over time of 120. You're probably thinking, I'm going to get a negative answer. Well, yeah, because it's a deceleration. Okay, so that's minus 36 over 120. So if I put that in, 3612, that's minus 0.3. Now, if you just did the gradient, 36 over 120, and you got 0.3, you didn't do the minus, that's okay. The deceleration is 0.3, the acceleration is minus 0.3, because it is a vector. So just be mindful of that. Okay, now this was chapter 9. So let's have a look at the rest of it. All right, so we've got what looks like a 6-mark question. So if you've got a 6-mark question with numbers, chances are you're going to have to use 2 formulas. So let's see what we got. Another train travels at a speed of 60. A constant braking force causes trains to decelerate and stop. So that's your original speed. That's your final speed. Okay, you've got a constant braking force, units are fine, and you've got the mass. Okay, so if you write out here, what have you got? So you got V equals 0, U is 60. You don't have to always write this out, but sometimes it helps just map out your ideas. You got F is equal to 27000, and you got the mass is equal to 240,000. Sorry. Okay, I've left the units out. There's no reason why you can't add it on. So calculate the distance S. So what formula do you know with S? You've got 2, haven't you? You've got S is equal to VT, distance is speed times time, and the other one you've got is V squared equals U squared plus 2AS. Now you're thinking, well, which one can I use? Well, if you look here, what formula do you know that connects F and M? Remember I mentioned it here. Which acceleration formula do you use? As soon as you get F and M, as soon as you see F and M, then work out F equals MA. So I would do F equals MA, put the numbers in, so 270,000 is equal to 240,000 times 8. Remember I said, if you're not sure what to do, at least do some calculation. If there's a calculation you can do, just get on with it. Just get on with that calculation. Okay, so now you've got to be careful here because it decelerates. So this should be negative. Okay, now whatever the answer I'm going to get, I'm going to put a negative sign in front of it, because when I put it into here, it'll be important because you've got the plus here. So if you have a plus and you put positive, it's going to be a different answer. If you have a plus and you got a negative. So let's work out A anyway. So that's 270,000 over 240,000. So put it all in. You get 1.125 meters per second squared. So now I've got A. So I've got A, I've got V, I've got U, I'm trying to work out S. So if you got V squared equals U squared plus 2AS. Now you're going to see why it's important, because V0, that means one of these terms you're going to have to go to the other side. And it's just convenient, A is negative, so this whole term is negative. So when you take it to the other side, it becomes positive. So you see what I mean? So 0 is equal to 60 squared plus 2 times minus 1.125 times s. Okay, so because it's negative, this whole thing becomes negative. I'm going to take it to the other side. So 2 times 1.125 times s is equal to 60 squared. Okay, so if you 60 squared is 3,600. Okay, so 1.125 times that's 2.25. 2.25 is equal to s. So then just put it in. Let's see. You got 1,600 meters. Okay. Now there is another way of doing this, but this one should be the one that pops in your head, because you see F, you see M. Work out an acceleration. Oh, you got a couple of you got a speed, you got an S. Oh, what do I know of acceleration and speed? Sorry, acceleration and S. V squared is u squared plus 2as. Okay. There are other ways. There's no one way to do it, so don't panic like, oh, can I use something else? You could do energy wise. It's got kinetic energy because of the 60 meters per second. So you work out the initial kinetic energy, and then obviously it stops. So the kinetic energy turns into something else. It turns into work done. So the kinetic energy, or the half mv squared, becomes Fs. So you could work out S that way, and you've still got 6 marks. Like I said, it's this is the one that should pop straight away into your head. F and M. F equals MA. Oh, I've got A now. I've got UV. I'm trying to work out S. Okay, so it's illegal for train drivers to drink alcohol before driving a train. So explain how drinking alcohol would affect the stopping distance. So affect the distance. So clearly drinking alcohol, that would increase reaction time. So we haven't explained yet reaction time, we just stated. Okay, and then if you increase the reaction time, you increase, and because it's a human, it's about the human, you increase the thinking distance. Okay, now why does the thinking distance increase? Because distance is equal to speed times time, and you've increased the time aspect. So this is us now explaining. Well, how does that affect the stopping distance? Well, stopping is equal to thinking plus braking. So it's not asking about the car, the weather conditions or anything. It's asking about how thinking affects stopping. Well, thinking and braking, they both affect stopping anyway. So that is 7.4. What they have not asked on this paper at all is momentum. F equals mv minus mu over t. Conservation of momentum. Impulse, or ft, is equal to mv minus mu. They haven't asked any of those. So, and they did ask that in 2023. So expect that sort of question to come up. Okay, moving on to question 8. So what we got here, so chapter 8 looks like a chapter 15 question. So magnets, magnetism, electromagnetism, motor effect, generator effect. So figure 13 shows some apparatus used by a teacher in a demonstration. Teacher moved the wire upwards between the magnets. The needle on the ammeter deflected, so it created a current. So this must be a generator effect. So what effect is this? So this is generator effect. Now, how can you tell whether it's generator or motor effect? Because those are two different ones. A generator will produce a current. That means there's no current in the wire originally. How do you know there's no current? There's no power supply connected to it. If there's a power supply connected here instead of an ammeter or a voltmeter, then clearly there'll be a current in the wire itself already. And the current in the wire produces a magnetic field in the wire. The magnetic field of the wire interacts with the magnetic field of the magnet, produces a force given by Fleming's left-hand rule. That will be the motor effect. But clearly there's no power supply here, and they moved it. Okay, so they've used motion to create a current. They've not used the current to create motion, which is what the motor effect is. So essentially, as soon as you realise generator effect or motor effect, which one it is, just blurt out the theory. So the theory, now if you haven't seen it, or you didn't turn up to the revision lessons, or you're not in my classes, then I will post the slides that I put on, maybe at the end of this video, just part of the recap, just for you to sort of go over it, or just go over your notes anyway. So explain why current was detected when the wire was moved upwards. So basically it's asking you, if you move the wire upwards, you've obviously got a magnetic field in between these, and here it'll be uniform. north to south in this case. So what does the wire do? The wire cuts the magnetic field lines, induces a voltage in the wire, or induces a PD, the other word for voltage. And if the circuit is complete, which it is in this case, then a current is produced. Okay, so let's put that in. So the wire cuts magnetic field lines, induces a voltage, or PD if you want to use that word, which is probably more suitable. And if the circuit is complete, then that means that current flows. And you need to make sure you don't say induces a current straight away, because you'll lose 2 marks there. So the teacher reversed the direction of the magnetic field. The teacher replaced the wire in its original position. The teacher moved the wire upwards in the same way as before. What was the deflection? So instead of the field going what looks like into the page, and it's coming out of the page. So if you reverse something, you reverse the results. So the needle will deflect. If it's plus 0.4, it'll now be minus 0.4. If you reverse the field and you also pushed it down instead of up, 2 reversals will lead to no change. Okay, if you did exactly as in here, teacher moved the wire upwards, but you double the speed that you moved it upwards, you'll get double the induced EMF, induced voltage, and induced current. So that would now be 0.8. If you pushed it downwards at double the speed, you'll get minus 0.8. Okay, milliamps. So just be mindful of the what ifs, and then they could ask. Yeah, that's pretty much what they can ask, isn't it? Like, what if you change this? What if you change that? What if you change 2 things? Well, that will cause no overall change, and so on. Okay, so then with the generator effect, there's 3 examples you need to know about. One is the AC generator, one is the loudspeaker, and the other is the dynamo. Dynamo came up 2023. Okay. So let me say it again. So AC generator, microphone, not loudspeaker, sorry. AC generator, microphone, and dynamo. Dynamo came up last year. Okay, AC generator has not come up. Okay, so this one is the microphone. Now, how do you answer these? You answer it. This is actually a pointless question. The actual answer to this is here. So the wire cuts the magnetic field lines, induces a voltage, the circuit complete, current flows. So, well, what's different? So when you come to the examples, this is pretty much the explanation, plus you need to write one more thing, and that one more thing is the context. So clearly the wire has got to move. This wire is going to move in between this magnetic field, which is fine. Well, what's going to cause it to move though? In this case, the sound waves are going to hit this diaphragm, basically a cone, and as the sound waves hit it and vibrate, it causes the cone to vibrate, so it causes the coil to move forwards and backwards. So therefore, the coil cuts the magnetic field lines, induces a voltage, circuit is complete, current flows. But then, because the direction of the motion is changing, it's a bit like me saying move it up, move it down. What you're going to get, a current that goes induced EMF voltage, and therefore an induced current to go positive and negative. So what do you call a current that constantly changes from positive to negative? You call it an alternating current. Okay, so let's put this in. So explain why the sound waves. So the sound waves, or vibrations of the sound waves, cause the diaphragm to vibrate. Okay, so because of that, the wire cuts, coil induces PD, and therefore current flows, because, don't forget, complete circuit. Okay, and then the coil moves back and forth, forwards or backwards, positives, negatives, whatever. So therefore you get an alternating current. Okay, so that is the end of this paper. It's not too difficult. So in terms of predicts here, if they're going to ask a generator question, they're going to have to ask you about the AC generator. They asked about the dynamo last year. So AC generators quite nice because they can link that to the national grid. They can then link it actually to transformers because they haven't asked a transformer question here at all. They didn't ask. They asked one last year, but more about the formula, but not about the structure or how it works. Why does it need AC? So something to go over your transformer theory. They did ask about the motor effect last year. Is about the loudspeaker. Okay, so with the motor effect, you've obviously got the formula for that, which is F equals BIL. You've got two examples, the DC electric motor and you've got the loudspeaker. The loudspeaker came up 2022, but there's no motor effect, 2023, no motor effect in 2022. So go over those. I'll add some notes to the end of this video, or I'll do a separate video and analysing this and going through it. So key things to remember, if we just quickly go through it, what I'm expecting. So this required practical. I'm not expecting this anymore. This is chapter 14, reflection refraction. So what I'm expecting for reflection chapter 14, I'm expecting ray diagrams, and expecting also, don't forget the other thing that's not been tested on chapter 14 is filters and colours. So expect that. Chapter 8, I'm definitely expecting vector diagrams, scale diagrams, working out the resultant using the parallelogram method, okay, or even resolving. So I'll go through videos on that, how to do that. Chapter 6, question 3 was chapter 16. Pretty much I'm expecting why something is a main sequence star in terms of gravitational force inwards is equal to the fusion pressure outwards. So they can ask you like what was the initial stages, what causes a protostar, why does it then become a main sequence star. Life cycle of stars, nice questions to ask. Redshift, they've asked 2 years in a row now. In fact, 2 years in a row, and what they haven't done is link that to Big Bang theory. So make sure you know why this is evidence for the Big Bang theory as well as cosmic microwave background radiation. This bit I'm not expecting to come up again, like fusion inside a supernova causing heavier elements. This one I am, so chapter 14, they haven't talked about, they've talked about pressure in liquids. They haven't talked about atmospheric pressure much, like how atmospheric pressure changes with altitude, explanations for and calculations. So I'll go through one of those or a past paper question on one of those on my next video. Should be within the next few days, if not tomorrow. Although tomorrow doesn't mean anything to you until I post this, I guess. So I'll give you an example calculation also of how they link rho GH to pressure equals force over area. So this is chapter 12, if I remember, or is it chapter 11? Just give me a second, so I'll just quickly have a glance. So what I'm expecting, yes, chapter 12. What I'm expecting from this one, which hasn't come up yet from chapter 12, P waves, S waves have come up. Obviously, this is the higher tier stuff. Uses of ultrasound, depth testing, properties of sound waves. So I'm expecting that because that hasn't come up. In fact, that didn't even come up last year. V equals F lambda comes up, but that comes up generically for waves. V equals F lambda is here. P waves, S waves have come up. I think P waves, S waves, if they can ask anything about this again, they'll ask a reversal of this. Like, there is a shadow zone. What does it tell you about the structure of the Earth? And this is all your knowledge here. In fact, this whole question is your knowledge. F equals MA experiment, maybe they could ask you a 6 marker, so just be mindful of that, because if you remember here, they haven't asked a 6 marker for that ever, or the last 3 years. They haven't asked a 6 marker for Hooke's law, but I'm expecting Hooke's law because that's a nice, but even either of those. Okay, ripple tank and string waves, I'll go through some calculations for that, but please watch some videos of these. Okay, these, just put them away. Maybe This one, they could ask you about cooling curves or heating curves, plotting some graphs. Make sure they're curves, they're not going to be straight lines. Okay, so this was chapter, I'm thinking, what was this? This was chapter, it was chapter 10. What they haven't asked about chapter 10 yet, which was all the higher tier stuff, is conservation of momentum, impact forces, what's the effect of time on the size of the force, i.e. think of like crumple zones, crash mats, seat belts, etc. V squared equals U squared plus 2AS. Expect these calculations, they'll always come up, so keep practicing those if you can. Go through the past papers. I've already put them in the classroom in terms of sections, so go through those. Again, this experiment, I don't expect calculations on this one again. If anything, it'll be a method, maybe a graph to plot. EM waves, chapter 13, I'm expecting a bit more maybe on the order, uses of dangers, and also maybe what could be really topical for this one is UVA, UVB, UVC, like descriptions, uses, dangers, where do and so on, and especially X-rays, how do X-rays work, and so on. So that could possibly be that one. Right, chapter 7, question 7, VT graphs kind of links in with, I don't think it was, kind of links in with forces. They haven't asked the terminal velocity question this year, or 2024, and they asked the terminal velocity question from what I remember. 2022 was the last time they asked as terminal velocity, and it's terminal velocity of hailstones. Now you're used to terminal velocity of parachutists, yes, I get that, but it doesn't matter, it's just a particle. Okay, so expect some terminal velocity questions. So maybe I could go through that, and also the graph for it, and also because they've asked you done a VT graph, maybe they'll give you a DT graph, and a DT graph with increasing gradients or decreasing gradients, and linking that to the accelerations, deceleration. So be mindful of that. Thinking distance, stopping distance, that comes up as quite straightforward, just knowledge. Calculations, yeah, they can be quite tough. Done generator effect, I'm expecting motor effect, or if they're going to do generator effect again, it'll be the AC generator. Okay, but if it's motor effect, I'm expecting DC electric motor, or maybe the loudspeaker, because that is the sort of toughest thing about it. And I think, yeah, so that was an example. They've done the dynamo for the generator effects. They've done the microphone. The only thing they haven't done for the generator effect is the AC generator. But besides that, I will do another video. But while you're still here,